series of the July lectures in physics. Now, before I begin, I would like to acknowledge that this lecture series and all preceding 55 lecture series have been held on the grounds of the Wurundjeri people of the Kulin Nation, that they have been the custodians of these lands for tens of thousands of years. We would like to acknowledge that their custodianship has been guided by a careful and scientific appreciation of the natural world. And we pay our respects to their elders, past, present, and emerging. So to kick off, it gives me great pleasure, and it's a great honor for me to introduce the Dean of Science, Moira O'Brien. Moira presides over the Faculty of Science, which is the largest and, in my view, the best faculty in the university.
In the universe.
Thank you for being here. It's a real pleasure to get to say something at the start of this lecture. So the July lectures in physics are a wonderful tradition that our School of Physics hosts annually. For 55 years, audiences new and old have gathered together on Friday evenings to learn and be entertained by our lecturers. Topics since 1968 have included the launch of the personal computer, which was once a very new and remarkable phenomenon. They've included how software help physicists understand what happens in the complex world that we live in. How things fly, why boomerangs return, the invention of the laser in the 60s, life on Mars, the physics of the Pathfinder mission, and physics of the didgeridoo. The tradition of the July lecture in physics is so strong and the topics so captivating that not even the global pandemic could stop them, and they quickly switched to online learning during the pandemic years. This year we're doing something quite special, a first for this series, an all-woman lineup of speakers. These women all work at the extremes of their field in their quest for new knowledge. And I'm delighted to have them share their scientific curiosity with us over the next 4 weeks. There is something uncomfortable about being called a role model, but it's also a huge honour. Each of these brilliant women who will present in this year's series is an example of what can be gained if we welcome diverse minds and skills into the field of physics, or indeed any field of science. Many of you will not be surprised that this is something that's quite dear to my heart and a core mission of the Faculty of Science. We refer to it as excellence through diversity, where diversity may be diversity in race, or gender, or cultural background, or ways of scientific practice, or many other things. And it is about bringing the most brilliant minds to the table to tackle the biggest challenges in our globe. I personally look forward to a day when it is completely unremarkable for a physicist, or indeed to be a woman, and when we're all just scientists doing great things. The theme of this year's lectures is Physics at the Extreme, and tonight's talk with Professor Elisabetta Barberio will be an extremely interesting one. Elisabetta is from our School of Physics and is the director of the ARC Centre of Excellence for Dark Matter Particle Physics. She will discuss the elusive world of dark matter and the extreme lengths scientists need to go to finally gain such answers about the cosmos. It involves working at 1 kilometre underground in the mine. Burton University's inaugural chief scientist, who will explore the dark, unseen side of the universe and how dark galaxies can be detected using next-generation radio telescopes. Our last lecture on Friday the 28th, will be from Associate Professor Katie Upshall from the School of Physics. Katie's research involves studying the most extreme objects in the universe, and she will discuss the life and death of stars. Stars do not live forever, rather they explode like a firework in a supernova explosion. Katie will explore how physicists piece together the leftover pieces using telescopes on Earth and in space. All four of these brilliant physicists is pushing the boundaries of human knowledge for the betterment of humanity. They are role models. They also happen to be women. With that, I am very excited to launch this year's July lecture series and explore physics at the extreme. Thank you again for joining us. Over to you, Mary.
Okay, it gives me a very great pleasure to introduce my colleague Elisabetta Barberio, who is Professor of Physics at the School of Melbourne. Currently, she is the Director of the ARC Centre of Excellence for Dark Matter Particle Physics, which is, I've heard it described as the ultimate gig in research in Australia. Elisabetta has initiated the construction of the underground mine facility at Stawell, otherwise known as SUPL. She has played an important role in the discovery of the Higgs boson at the Large Hadron Collider, and earlier in her career made fundamental contributions as a researcher at CERN, which is the International Particle Physics Facility in Europe. And tonight, Elisabetta Barberio will talk about the search for dark matter, exploring the universe a kilometre underground. Please welcome me. Please join me in welcoming Elisabetta Barberio.
Thanks a lot. Thanks a lot. Can you hear me? I think I need to adjust the microphone. I think it's better now. So thanks a lot, and it's a pleasure to present my research and what is going on with the Centre of Excellence, is this new underground laboratory that people in Victoria may have heard a lot, and the experiment that we are going to do there, and how we're going 1 kilometre underground to uncover what the universe is made of. This is one a mural that we have here in the School of Physics in the basement that describe a little bit what I'm going to present in the story. So we go from what the universe is made of. I have a, okay, I think.
Can you put the microphone?
Yeah, I can put the microphone. It's better now? Yeah, I know I have also a problem with the microphone. It's better now? So I will go from what the universe is made on to Stawell Underground Lab. So we start, and I think the question that my research underpins what the universe is made of, and I think it's a question that everybody is asking themselves. And I would say that perhaps the most astounding discovery of the 20th century is that the majority of the universe, so the table of the element that we know here, sorry, it's just here, it makes only 20% of ordinary matter. All the rest of the matter in the universe is an unknown substance that we know is there because there is gravity. Gravity tells us that it's there, but we cannot see. That's why we call it dark matter, and we don't know what it is. And so we are in this quest of understanding what the majority of the universe is made of. And this is a big question in science. The universe is full of dark matter, and now we need to understand what it is. So how do we know, first of all, that dark matter exists, and we are not searching for something that really does not exist? Well, we know that dark matter exists because of gravity. This is, we can calculate using the gravity force. This is a diver, how fast it will go when it touches, and we know G, that is the, sorry, it's just using We know g, that is the constant of gravity, so we can calculate the speed which this diver will hit the water, knowing at which height he will start diving in the water. So this is well-known physics, and it's Newtonian physics, and so we need to calculate. So what happened now, and I'll show it, we are in the galaxy, and our galaxy rotates, and when we look at the velocity of the star in our galaxy that rotate, we have that, we expect by gravity that the star that are on the periphery of the galaxy rotate around the center of the galaxy much, much slower than the one at the, much, much slower than the one at the center. But when we do our measurement, we notice that is happening the opposite. So the velocity of the star at the periphery of the galaxy, it doesn't slow down as we expect, but it gets constant. And it acts as we have more material around our galaxy that we can see. And this is the first observation. It's very old. It's more than 100 years old, but people took a long time to verify that this was done. And so this is what we expect. This is the physics, the graph. This is the velocity, the center of the galaxy. That you see as we go far from the center of the galaxy, stars first go faster around the center of the galaxy, and then they expected that the velocity should go slower. And in reality, what happened is that what we observe, the velocity is not changing. That means that we have more material in the galaxy that we can see. And this observation was confirmed. First was done, as I say, 100 years ago, but the person that really did it was a woman, and she really, observing the star, confirmed that indeed in our galaxy there is more matter that we can see. And this is the beginning of understanding that we have what the things as dark matter. We have many other indications that we have dark matter, because light in the space doesn't travel straight. When we have a galaxy or a star and so on, they produce a warp in the space, and so light follow. It's like going up on the mountain, up and down, so you move in this direction. And this is create optical illusion. It's like when you go and you see mirror, you know, in a carnival, you got mirror that, you know, change your aspect ratio, and that's what you can see. This is you can see optical illusion. This is a sculpture done by an artist that wanted to represent the optical illusion that we see due to dark matter. And then when the astronomers look in the sky, they see interesting stuff. Like, for example, this is dark matter fingerprint. This is not a joke. This is not invented. This is a galaxy. And you can see this part over here. These are the original galaxy that you see. But then you see all of these kind of stretched galaxy. And this is the same galaxy. And because light goes in different direction to reach us and do different paths, we see this kind of interesting figure. And this is tell us that we have dark matter. So what do we know about dark matter? This is the list of the particle physics zoo particles, fundamental particle. We try all the fundamental particles. None of them can explain dark matter. And so if dark matter is a particle and is the majority of the universe, we need to know what this particle is. And it could be one, or it can be, you know, very complex. It can be many particles. It can be a dark matter universe that we don't see and we need to discover. And so our job is really going and travel in this unknown universe, and this is our fundamental question, what the universe is made of, and we don't know. And so now we are entering in an area where we know very little. Well, we have some parameter to look, and so the issue is like, how do you search for and how you find for something that you don't know what it is? So there is the challenge. The challenge is that we have parameter, you know, we know that galaxies are kept together by dark matter, and so dark matter must have a certain amount of mass to keep together galaxy. And when we look at that, we know that the mass of this particle can span order of magnitude along the mass spectrum. Here I have what we call TeV, EV, etc. I'm a particle physicist, so all my measurement except distance is calculated in terms of energy, so it's energy. But as to give you an idea of how big, how much will weight this dark matter, we see that when I start PeV, which will be a dark matter particle that will have the mass of virus. And then I go lower in the mass, I go to particle with the mass of a DNA molecule, of a nucleus, and then proton, electron, and then smaller and smaller and smaller. And the small particle that we know in the universe is the neutrino, but we can go even smaller. Now, what I will concentrate is in the area that we call particle-like. So when we go underground to see this particle, the other particle, the wave light, we don't go underground, but we construct particular kind of radio antenna to see them. But this is maybe for another July lecture. So what is the challenge? As I say, there is this big range of masses, and there is a lot of hypotheses of what dark matter can be, and there are thousands and thousands and thousands. And so what we do in our search, we categorize as probable, improbable, maybe, I really don't know, I don't have any clue, and no. And we go through and look at them, and we start with the most probable, and we search, and then remove the most improbable. We really as a Sherlock Holmes, and if at the end we find that the most improbable, it's what we look, we are even heavier, much more happier, because obviously we have a lot of work to do also to reset our understanding of physics. And so this is where our, there are many possibilities, so we need to look in many different ways. So how do we look in dark matter in the particle-like? Just generic, this is, you know, there are different, what we call discovery machine or experiment that look for dark matter done in different way, exactly because we have many possibilities. But all of them are based on one thing. If we look at our galaxy, this is the galaxy, as it will look like our galaxy from the outside. It's embedded in a halo, you see this blue hue, of dark matter. So you can imagine that our galaxy extends much, much larger, the mass in our galaxy, than what we can see. And this blue hue is our dark matter. And you can see it's really like a big sphere around. And the other thing I can say that you can think about the dark matter like many, many particles that don't move very much. And we, on the contrary, as we rotate around the sun and the sun around the galaxy, we are the one moving through a sea. So like we can think about, we are on a small boat on a sea of dark matter. And so you can see here, if you are on Earth, we have this dark matter wind that reaches us, because you can think about like when you go on a bicycle, you know, even if there is no wind, as you start pedaling around and go you faster or slower, you feel a wind that is not that you have wind, but you are moving with respect to air. And so we exploit this dark matter wind that reach our Earth and pass through Earth and pass through us to discover, to understand what this dark matter is. So what is the hunt of dark matter? So we use this dark matter wind. So we put our detector, our discovery machine, thinks is a part on Earth, somewhere on Earth, and then we're waiting for the dark matter wind to reach our detector, interact with our detector, do something with our detector, and we hope that our detector, our apparatus, call it our discovery machine, will see something. And so this is how we see the invisible. And obviously, how do we decide which kind of discovery machine we build and how we build it? This depends, as I say, on this search for the most probable, the less probable kind of hypothesis. Now, why we don't see dark matter every day? You know, at the moment, as we are here, as Earth goes around the sun, there is a lot of dark matter passing through us like that, you know, and not interacting with us, so we don't see, we don't touch, we don't smell it. Why? Because the probability that dark matter hit an atom and do something with it is very, very small. So for example, if I have one dark matter particle that I enter here, and I want to know what is the probability, I want that this dark matter particle interact with matter with the probability is 1. Say, I want that interact. And how much matter I need to put there because the interaction happens, well, I need to produce, for example, a block of lead that is 1 light year long to be sure that I see. So you can imagine. You know, it's very, very small. But how can I build a detector that is 1 light year long? It's impossible. However, as we know, there is a huge amount of dark matter in our galaxy, and there are many, there are 1 million of particles per year that can reach a detector that is about 10 centimeters, 10 to the minus 6 light years. So if I have a detector of 10 centimeters of diameter, I have 1 million of particles, I'm sure that something will be seen. So I have enough collision of the dark matter particle with a normal particle that I will be able to see. This is posed the challenge. Now we go a little bit of numerology. So if I look at the dark matter particle and how frequently this dark matter particle interact with normal matter, I have that I expect 1 collision per day per 10 kilograms of matter. It's not much. And then if I look at everything that can interact with matter around me, that is mainly radioactivity and other stuff, well, I have that my background, the things that mimic dark matter in my detector is all the radioactivity, the natural radioactivity around us. And we will see when I see radioactivity, it's not that I'm speaking about large amount or a very small amount. And then also the cosmic ray that bombarded us. And here, just to give you an idea of the and do numerology that we are going to look, if I look, you know, this is the activation, so that means that for any source, you know, how radioactive is the source, depending on how long my radioactive element live and how many atoms I have. So if we look at that, how many becquerel, how much activity we have in our body, because radioactivity is everywhere, because every element in nature, very few elements in nature do not have what we call an isotope that is radioactive. So very, very few. All the other, they have always a counterpart. That means an isotope, something that is the same element, but with different number of neutrons, and this is most of them are radioactive. So how much radioactivity we have in our body? Well, we are made of carbon and potassium, and so you can see that we have 400 becquerel of potassium-14 and 4,000 becquerel of potassium-40. And how many radon? Radon is another radioactive gas. It's a monoatomic gas. It's an element. We have in air that we are breathing over here. Well, in 1 cubic meter of ground, radon atom, we have 7,000 atoms per square meters. And how many plutonium atoms and other radioactive elements per kilogram of soil? Again, we got few of them. So you can see that we have a lot of atoms, but the radioactivity that comes from them with respect to all the soil, because yes, are many atoms, but if you go are just milligram or microgram, so it's very small quantity, is there. And so everywhere, everything we do, everywhere on Earth, every element has a tiny amount of radioactivity, and so we need to deal with that. So the challenge is how we distinguish dark matter from interaction with the matter with our detector from all this radioactivity that surrounded us, and also from all the radioactivity that comes from the cosmos. In particular, the sun expels a lot of proton every year. They travel every day, every minute, every second. They travel to Earth, they interact with our atmosphere, and they produce a lot of what we call ionizing particle, a particle that can interact with us. And so every second, you can say every day, we have 10 billion of this cosmic ray that reach our body. Now, if we look at the dark matter, the issue is that we have 1 billion every day passing through our body. However, However, of these 10 billion a day that arrives in our body, most of them interact with our body. We are bombarded by radiation from the cosmos, and we have evolved because of this radiation from the cosmos. But of this billion a day of dark matter passing through us, only a handful of dark matter particles interact with us. We remember there was one interaction per day per 10 kilograms. So if you have 50 kilograms, you have 5 with respect to billion. So you will be able to see dark matter. So what we do is we go underground, quite deep underground. And so what happened underground? Well, of these billion arriving per day and colliding with our body, underground, only a handful arrive 1 kilometer underground. So we can shield it completely, this contamination from the cosmic ray. And dark matter, well, dark matter, as I said, doesn't interact very much with us, so it doesn't interact very much also with all the ground above on Earth. And so if we go 1 kilometer underground, if we have a billion a day and a handful, dark matter don't get blocked by the rock. So if we go underground, we are in an environment where at least cosmic rays do not annoy us. And so it's very convenient to go and build this discovery machine underground. However, once you're underground, we discussed already, there is radioactivity everywhere, even in our body. Every time we eat a banana, we increase the amount of potassium-40, that is a radioactive isotope in our body. And this isotope over here, or carbonium-14, they emit gamma ray, they emit radiation. And we get this. This is natural, don't worry. This is really how we live every day. And this amount of radiation is still too much for our experiment. It's still too much. If we go too close to our dark matter machine with our body, well, we will again be in a situation that we will not be able to see dark matter because there is too much, we are too radioactive for the dark matter. And so what we do, well, we go underground and we embed our detector in what we call a shielding. So can be lead, can be a passive material that you put around with very low radioactivity and shield all the radioactivity that comes. And then you can put something that we call a veto, that when you see one particle, normal matter particle, the pass-through is giving us a signal and tells what we are seeing here is really not dark matter, but a normal matter. And you can see exactly, if you are, for example, underground 1 kilometer, so you have also the radiation, for example, from the rock again, and you have plutonium, uranium, thorium, argon, etc. And this is normal, as we discussed in the soil. So given all of this, so we go underground, we need to shield our experiment for the radioactivity, but we also need to be sure that our experiment is built of ultra pure material that contains very, very little radioactivity. And then when you transport, when you expose to air, obviously, radioactivity that is in the air contaminate your stuff. So what we need to do when we build the element of our detector and then we bring underground before we put them together, we need to do what we call precision cleaning. So we need to use a procedure that, for example, if you have a metal piece, will be etching the metal piece, or other procedure with chemical or with water or with air, to be sure, 100% sure, that we eliminate all the radioactivity, the air of the dust of the transportation produced. And here, in this particular part, you see here in this part this is a photo. This is not a bad photo. This is inside a clean tent, and this is not taken during pandemic or in a hospital. This has been taken in Grand Sasso Laboratory, and this is one of the SABRE North vessel where they were cleaning. So you can see people with asthma suit, very clean. There you will see they will have a mask, and this is where cleaning everything. After you clean everything, you need to assemble, and to be sure that you do not contaminate anything, you bring your element of your detector, you store them in nitrogen, because nitrogen doesn't have any radioactive isotope, and so in a nitrogen environment. So you assemble in a nitrogen environment. And sometimes you can assemble before and clean, and depending how your element need to be in, sometimes you need to enter in this nitrogen environment where you have your apparatus to bring pieces and collect together. And this is the LZ experiment, in which they are mounting the last piece of the detector, dark matter detector, and they went in this tent that is full of nitrogen. And to work there, these are oxygen bottles. So they went snorkeling. You can see here the snorkel, you can do the snorkel, because all the environment was full of nitrogen, and so most probably some of our students will need to train as diver to do some of the operation on the detector. So this tells you the length we need to go to be sure that no radioactivity and no contaminant are there, even the dust or the air, so everything is there. So this is a very physics of the extreme already there. This is done. This is another experiment. This is SABRE. This is another experiment, but when we are going to mount underground, most probably there will be some of the part that we will do there. So now we go further and understanding. Now that we have our super clean detector, and we went to precision cleaning underground, and we screen all the material, and this is all another story, because we want material with almost no radioactivity, so we need to work very closely with industry and chemical engineering and chemistry to produce that. We need to understand what kind of signal I need to look for. And the kind of signal that we need to look for is a signal that is related to the fact that Earth goes around the sun, and the sun goes around the galaxy. And I see if I can start the movie. It's there. So you can see over here, we have the sun that goes around to this galaxy, and Earth that goes around the sun. And this velocity is 220 kilometers per second. We go very fast. And you can see that depending on the position of Earth, the velocity can be faster in this here when we are in December, and then slow down here and the minimum is in June, and they go there. Now, this is not the full story. So June, you see, is the maximum, and then it slow down in November or December, and then you go there. Now, it's not the full story. If you want to see the full geometry, there is an inclination of the sun with respect to this trajectory around the galaxy, and of 60 degrees. And so if you put your experiment on Earth and you count how many dark matter particles you see in June and November, you will see that in June and November you count a different number of particles, because it's like the wind of dark matter will be slower in June and faster in November. So it's like when you go in a bicycle, you will feel the wind when you go faster, so in November, and slower when we are slower in June. And so we are looking at the difference of how many particles our detector counts in the different months of the year to be sure that this gives us a signal. And how the signal looks like? Well, the signal here looks like that. This is, you see, many years. And this is, you see, the rotation, the velocity that goes slower and faster, so this is the number of particles. You see here that is November minimum and June is the maximum. You see here that you have this kind of graph that gives you modulation, a waving function. And this is the fingerprint of dark matter has been discovered. Your detector, see, this apparatus has this is the number of dark matter particles they see in June, and this is the one they see in November over many years. And if you see this modulation, this is the fingerprint of dark matter. So did we see dark matter? Well, there is an experiment in Italy that is called Dama Libra that using 250 kilograms of ultra-pure sodium iodide crystal. Sodium iodide is a salt, and if you put in water, it melts immediately, that operated over 20 years, and for 20 years has been seen this modulation signal. And this is important because other experiments, they use different targets. So they don't use sodium iodide, they use xenon, argon, and so on, did not see the signal. And the other experiments do not do this kind of looking how it changed the signal with the season. And so it's very important to really test the signal. This is the only signal, the only real signal in particle physics and in the world of really what a dark matter particle is. And this is so important, and people are so looking on, that you can see all over the world the amount of dark matter experiment that exist, of sodium iodide experiment that exist. So there are many of them. All this one correspond to an experiment that wants to reproduce the gamma modulation. However, checking the gamma modulation is not easy for many reasons. First of all, because we need to reproduce the same purity of that experiment, and in particular, the sodium iodide crystal are incredibly pure, and to be able to reproduce is a lot of work, because obviously every experiment keeps their secret, because obviously everybody is in competition. And the other thing is that there is a suspicious, there are discussions that could be that what they see is not a dark matter signal, but a seasonal variation of cosmic ray. There is still this handful of cosmic ray reaching down, and they change, the amount of cosmic ray change with the season, because change with the depth of the atmosphere. And so there is this suspicious there. So the only way we have to detect and discover dark matter and confirm the signal is to put an experiment in the southern hemisphere and see if we see exactly the same kind of modulation, the same curve, because if it's dark matter that produces the curve that we measure in the northern and southern hemisphere will be exactly the same. If, in the contrary, is a seasonal effect, remember, northern and southern hemisphere have different seasons, so I will have something that is the opposite. When in June for them is the maximum, that is the up, we will have, on the contrary, the down. And so we refuse the experiment. So it's very important, as I say, a lot of people are looking. And the interesting thing is that we are the only one in the southern hemisphere. There is nobody else. And the other things we did is that not only put a single apparatus here and say, okay, we put also another one in Gran Sasso, and we will work as a twin experiment, taking data together, and check, because obviously we'll have the different season, our count of dark matter as it goes over the year, and see if we see the same things, both of us. So we discovered dark matter, and obviously we celebrate. Or if we see the count go opposite, when we see the maximum, the maximum of the collision, and they see the minimum of the collision, they see the minimum. The collision is a seasonal effect that we did, and it's interesting because nobody, up to now, nobody could find which is the seasonal effect that they are seeing. So there will be maybe interesting physics there. Not as exciting as dark matter, but it's interesting. And so to test Gamma Libra, what happened? This is the signal. Is a dark matter, as I say, signal or a variation. Well, we can see here, we need a southern hemisphere perspective. This is very important. And beside Gamma, I must say, beside this experiment, if any experiment in the northern hemisphere see a signal of dark matter, the next step that they will do is measuring this kind of variation during the year to see really is that dark matter. And then you need the southern hemisphere to confirm that this variation is not a seasonal variation. So no matter, even if Gamma may not be the right signal, whatever is happening in the future about dark matter, the southern hemisphere will be crucial. Then we need to produce the ultra-pure detector, cleaning, part, and so on. And then we have the similar condition in south and north. And so this is where the adventure of the underground lab and SABRE started, because the SABRE experiment is the first dual experiment in the world, and we will have a northern counterpart here in the Gran Sasso laboratory on the Apennine in Italy, under the highest mountain. And to enter in the laboratory, you enter in a road tunnel, so your Laboratorio Nazionale del Gran Sasso. It's here. And then there will be us, and Stawell Underground Lab. So this was when you enter in Stawell, you can see that. And we have the Stawell Underground Lab that we call SUPL. And this is where we will pose our part of the SABRE South. Obviously, LNGS, the laboratory in Italy here, you can see is one of the largest in the world. He's more than 40 years old. This is the underground lab. You can see a lot of cavern, so you can see how big it is. And this is the site oversight the laboratory. As I say, it's more than 40 years old, and obviously it's grown up and done. And you know, it's one of the biggest one, and they are our partner, and they support us quite a bit. And you can see on the red triangle where they are. And then this is our underground lab, SUPL, that is here in Victoria. You can see here, he's in Stawell, it's about 300 kilometers from Melbourne, in the Stawell gold mine. And you can see here the entrance of the Stawell gold mine. And we are at 125 meters underground, about kilometers underground. Here in this part of the mine, this is the surface, and here, if you people are interested in geology, what it is, we are in a dome of basalt, so it's quite stable, and non-radioactive. We choose the less radioactive part of the mine. As I say, soil is radioactive. And how we reach the lab? Well, this is a mine that has a decline, so there is a road that you enter here, and we have a 9 kilometers road that it goes like in circle here. You can see this helical there, not really an helical, like that one is a little bit less geometrical because it's a mine. And so we have 9 kilometers. We drive 9 kilometers from the surface to the lab to reach the lab, and it takes about half an hour because obviously it's a dirty road and with a steepness that sometimes reaches 7%. And this is where we build the lab. The lab has been what we call stage 1 has been completed August last year. And this is, you can see the lab is about 30 meters long and 10 meters wide. And here where the experiment that we want to use to reproduce DAMA, the SABRE experiment, will be located. So you can see here the lab, the largeness of the lab with a lot of people during the inauguration. And you can see outside the lab. So we will arrive here after this half an hour drive with our equipment. I'm not going to describe how long it will take to build the equipment and all the pieces, because it will be another talk by itself, but we will need to bring every single bit through this road. This is a tunnel of 5 meters diameter, more or less, and some places a little bit smaller, and bring all this, all our stuff, including the shielding, the things that we will envelope our detector. These are more than 200 tons of steel, down and build the experiment down. And this is how the physicists will go and dress. This is me dressing to be ready to go underground, and this is what we do. So you can see here, so we will arrive there with our equipment. In this part here is we call anti-room. We will clean our equipment, roll it inside here, put under a clean tent, clean it, put in a nitrogen environment, and if we need to do anything else, put on a snorkel and the oxygen bottle and go in there. So now we speak about the SABRE experiment that I discussed. It's the SABRE South collaboration, so the Australian collaboration. So you see here all the universities that are involved: Adelaide, INU, Melbourne, Swinburne, and Sydney. And we have also a Japanese collaborator that is coming online. This is how it looks like the experiment, the vessel that is sitting now, part of the experiment, in one turner in Swinburne, the Swinburne University's campus. And this is the photos of the SABRE collaboration that in meeting that we had a stall in November in Victoria, and this is our pin-up part. So this is the SABRE South experiment. The SABRE South experiment here is 4 meters high and 4 meters, is a cube of 4 meters by 4 meters, so it's quite large. And this is the various element. The element that we'll see, the dark matter, are this crystal, this pure sodium iodide crystal, and now in a minute I will tell you what they are. And these are hosted in ultra pure copper enclosure, but there is almost no radioactivity, and immersed in a liquid scintillator called liquid alkyl benzene that is nothing else than dishwasher solvent. So that has been purified to remove every kind of radioactivity. And then everything is enveloped by the shielding that are steel and plastic shielding, and they weigh more than 200 tons. And then I'll tell you exactly, I use again a movie here. I see if this is the crystal, the sodium iodide crystal, how it looks like, and the hand model is filled. And here what's happening when a dark matter particle hit one of the, for example, the sodium atom, you see that they produce a light that is seen by our detector, and then you see, or another detector, but you see that the detector, the liquid scintillator, the dishwasher detergent that is around, don't see anything. However, no matter how we go pure, if there is a contaminant like potassium, potassium is everywhere, we cannot reduce, and is a potassium radioactive decay in our detector, we see again a light as dark matter. But then we have all this dishwasher powder that will, this liquid alkyl benzene, that will be receiving this particle and will give a signal. And here there are the people of Veritasium, I don't know if you know them, that show the vessel. And so you can see the vessel will do light, and our vessel will see, this is how we see dark, we see that this is a photon and not this is the vessel in real life. If we see the liquid alkyl benzene and this detector over here illuminated, we know that this is a potassium decay and not dark matter, and so we can discard. Potassium is very important because potassium is it's very difficult to eliminate potassium when you do sodium iodide crystal, and you need to go for big length to eliminate this potassium, and this potassium 40 is radioactive and can mimic dark matter. And so you want to eliminate or keep to the minimum this potassium. You cannot put to zero, so that's why we use the dishwasher detergent to see what the emission from this potassium, and when we look that we have a signal in our crystal and a signal in our scintillator, we remove it because we know that it's not dark matter, and so we increase our chance with the see dark matter. So this is a little bit of the element that put, so we speak about this highest, the sodium iodide crystal. These are the highest purity sodium iodide crystal ever made. We did some together with Princeton, was more than 7 years of R&D. We also use the phototubes. These are the detector when we have the light inside our crystal. They see the lights and they tell us there was dark matter, also using the photoelectric effect. And then we have a lot of engineering because this business is 4 meters high, 4 meters wide, and on top of that we have this crane to insert this sodium iodide crystal inside the vessel that is other 4 meters high. So it's a big beast. And so we have a complex engineering design also there. So here the vessel we have already, as I say, is in 1 Turner, you can see here. And you can see here also our PhD student doing the course for working at height and working in restricted space. And this was a dummy that was sent at the bottom of the vessel, and the students were supposed to rescue them. Some they succeed, some on the contrary they stab by mistake, and so I don't think they passed the requirement to be working on height and working at restricted space. So you can see also, you think a physicist work in a lab, not only we go in a mine, we also do, this is a tradie, this is, after this training, you can clean your gutter, or you can go under your house and clean other parts. And so, in fact, some students put their hand up because they say they will make happy their grandmother happy, so they can clean the gutters of their grandmother's house. So here is inside. Oops, sorry, I need to go back. I don't know if it doesn't seem to go. So this is inside the vessel. Sorry, this is a movie, but it didn't work. That's fine. That we enter in the vessel, and this is the steel vessel. And then we wrapped it up with Slumir to increase the amount of reflection that we have from the vessel, so we can see more this potassium stuff that annoys us. And this is what our sodium iodide crystal, the super crystal, do. You know, this is about 3 kilograms sodium iodide crystal. So this is the core of our part, and this is one of an oven that produced the crystalline and purified before we crush it and build it and grow again, so we have very high purity crystal. And this is how you manage, again, in a clean room, in a clean box, in a clean room. And here you see the gloves. In reality, this is double glowing gloves. So I think only in biology departments they have all the same things. It's like working against microbes or so on. And so how much potassium-40 that is evil for us? So if we look at the banana, we have 360 milligrams of potassium for, that is about 100 becquerel per kilogram of potassium for banana. And our crystal have 10 million less potassium-40 in the crystal than a banana. So, and to do this, as I say, has been a quiet part. And so this is key for our experiment. So to show that we are building the experiment where we are with the experiment, here are the various elements. Again, you can see a lot of people with asthma suit and with the mask, not because there was COVID, there was mask because you don't want to breathe on your detector because your air that comes from you is contaminated with radioactivity. And this is, you can see the various elements and everything glowing with the gloves and so on. This is not the real part. This was just a prototype, but as soon as we go to some of the real part, everything needs to be extremely clean. And then the shielding, we use steel, but one of the other popular part of the shielding is lead. And the popular part, if you are in Italy, of this lead for the shielding is Roman lead. So Roman had a lot of boats, and they were not very good at the time, and they were sinking a lot. And they had baluster, and the baluster was made of lead. And so there is a lot of Roman lead sitting on the bottom of the Mediterranean, especially around Italy. And people, you can see here, they are going and look at this big ship that sink because are archaeologists. And they bring up the baluster of this ship that was made of lead. And so there is an agreement in Italy between the physicists that work in the lab, like in the Gran Sasso lab, and the archaeologists that what happened. This lead has been under the water for millennia, and so does not contain any very little radioactivity, if any radioactivity at all, because the lead-210, that is a component of the lead, an isotope of the lead that is radioactive, has been all decayed. There's a half-life of 100 years, and there has been already 2,000 years that is down. And so the physicist wants this lead for our experiment in dark matter, and so they agree with the archaeologists that normally the baluster is like a kind of pyramid, a Toblerone, look like a Toblerone. So the physicist gets the inside, and the archaeologists keep the outside where there is the print where the ship was, or the company, or various things. And so this is what we call Roman lead, and so you can see that we need to go not only underground but also underwater to source our material. And so this is called Roman lead and is low radioactivity. So you can see here where we go. So after all this adventure, underground, training as a tradie, learning how to dive, and also going underground, dive not only to get our Roman lead, but also to build our experiment, where we are with SABRE. We did quite a bit. It's a very complex experiment. It's a you see, it's big, there is many components, and this is what we achieved up to now. We have our big crane, this is about 4 meters high, to put our crystal inside, and it's done in such a way that will be done in a clean environment. We have all the acquisition of data and so on. We have our industrial control framework, in particular to control the nitrogen that will surround our experiment and the liquid scintillator. So it's a very large control as in part. We have a computer that computing, so we take the data that get recorded in the mine. We ship a Melbourne Uni, and Melbourne Uni has the record and all the collaboration go. And then we have all the chain, and so we are doing quite well on the construction. Here, we hope that now that everything is ready, we can start bringing things underground, the assembly. So you saw the vessel before. This is the crane before. This is in One Turner in Swinburne. This is here in the School of Physics over there. And this is the liquid scintillator in a container. This is by the way, I forgot to tell you that these are 15 tons of liquid scintillator that will go down in the part. There's a lot of washing cycle of your washing machine. This is another element that is sitting on top of SABRE to reject the handful of cosmic ray that still reach down. That is the muon system, and the length of this muon system is 4 meters. And here we have this glove box, so because it doesn't matter if we are in nitrogen and so on, we will have again another glove box. A glove box is a very pure environment, flux with nitrogen, where we will insert our crystal inside this enclosure of pure copper that we will put in our experiment. And we are ready to bring this underground and start construction. So how it looks underground, this is our photos taken from the Gran Sasso. So what we will do, where we will build the big tent around, you can see, asthma suit, again, everything is covered. And this is one of our colleagues from Adelaide, when she was in Italy, cutting this white sheet that we put in the vessel over there. And this is the atmosphere that is clean, and as soon as we finish cleaning, this will be closed and will be fluxed with nitrogen. And when you enter in, you need to use the oxygen bottle. I'm sorry, I went on the wrong direction. And so what happened once we put everything together and we start data taking, we will have that after 2 years of data taking, we will be able to see if we DAMA discover dark matter, or say, no, you see a seasonal effect. And you can see here, this is our projection, our simulation of what we see, of the probability that we see a very nice modulation as DAMA. The difference from DAMA took few years, 20 years. Okay, they continue to see the signal, but take a few years to see the signal, because we have a much higher purity. Our crystals are the best in the world. We have the ability in a very short time to see this modulation and see yes or not. And so as soon as we're done, I hope in 2026, 2027, we will be able to come here and say, yes, I hope, and we are all happy. And so, wrapping everything about the journey of dark matter, as I say, in the 30s, 100 years ago, Zwicky had the first idea. He noticed that the rotation of the galaxy didn't make sense. They started in the galaxy, and so eventually there was Vera Rubin that in the 70s pinned down that this could be missing mass, this could be this dark matter. And then DAMA is an old experiment. In 98, DAMA claimed the first signal of dark matter. And then you can see here a lot of other experiments. These are from satellite, underground, and so on, that start hunting for dark matter. And, in the last, this is expiring this next year, 2024. I need to redo the slide. Is that a possibility that we can see dark matter behind a corner, and we are still hunting. And it's very exciting. It's a very exciting field of research, because if you think about, you know, we are taking part. At the moment in physics, we thought that it's like when physics people discovered quantum mechanics. They thought that everything was solved, that they knew everything about the universe and how it worked, and then quantum mechanics pop out and they change the vision. Now we are in the same. We think that we know everything. We have this, you know, as a particle physicist, we develop what we call the standard model of particle physics, this theory that is tested at the per billion level. But then we have that the majority of the universe is unknown, and we try to understand what it is. So I think it's very exciting to be in physics right now in this particular kind of research, because we are on the brink of start exploring this unknown universe, and we are going to see, you know, what the universe is made of, how it's composed, because it can be a single particle, it can be that we have an entire universe that does not interact with us and coexist with us, as complex as we are. So very exciting time. Thanks.
Thank you very much, Elizabeth, for a very clear and thought-provoking and exciting talk about particle physics. There's, I presume you're available for a few questions, so does anyone have any questions? There's one over there.
G'day, that was pretty good.
Thanks.
Look, if 20% of the known universe has the 116 odd elements that we know of, and the 80% of the known universe has this dark matter that we don't know of, but you need a lot of lead in terms of trying to get an interaction. How do we know that the unknown amount of elements may be less or more of the known elements? In particular, as your last statement made, it may coexist in some sort of outside, which I can't even conceptualise what you just said. Yeah, so when there is an impact underground and the sodium crystal emits, can you actually determine what that element is?
Yes, in the sense how we build this experiment, you know, the crystal emits lights, and because dark matter interacts so little with the rest of matter, in our experiment, if the dark matter experiment interact with the crystal, will interact only once. They will not interact with the crystal around, because the probability is almost zero. It will not interact with the dishwasher detergent. In the contrary, if we have something radioactive like potassium, but can be lead, can be anything, what will happen? I will see a signal in my, I will see light in my crystal, and light also in the dishwasher, in the lab, in the liquid scintillator. So I know that this cannot be, because normal matter interact a lot with us, because it's normal matter. I don't know if I answered the question. So if it's normal matter that we are made of, there will be seen a light in the liquid scintillator and in the crystal. If it's dark matter, there will be the light only in the crystal.
But if it's so abundant, why is it still that hard?
Because it interacts very little with us. Does not emit light. You know, to interact, there must be a force.
Oh, so the force is very weak.
The force is very weak.
Question here.
Thank you very much. Where do we expect the research of dark matter to be, say, in 100 or 1,000 years' time?
I hope that we discovered. I hope we discovered, and when we discovered, we will have our detector, our experiment to be understanding dark matter. Otherwise, if we don't discover anything, means that dark matter coexists with us, but there's really no interaction. So it's like a parallel universe. Our ghost.
correct, first of all, that you expect it not to interact at all and not to decay? And if that is the case, do you expect it to have an equivalent magnitude of weak force belonging perhaps to another model? And associated with that, the early universe, when these particles were created, did they in fact self-interact then and decay and reduce in number? Because obviously they're very stable particles.
Okay, so WIMP means weakly interacting massive particle. We call is something that, WIMP, this weakly interacting massive particle, was interacting weakly. And I would say this is an old name that we still use for, most probably the best way to use now is WIMP-like. So they are massive and they interact weakly, but not with the weak force. The idea at the beginning was that there is this particle that interact very weakly with the weak force, and they can be introduced to explain some cosmological problem, like that for the evolution of the universe, and on the other side, solving some particle physics problem about how the universe came about. Unfortunately, experiment excluded that fantastic theory we really loved because it was solving many issues, but still we believe that a massive dark matter particle can interact not with, we call weakly, but it's not the weak force, it's really different kind of interaction that is becoming much more weak, because in practice is what we are seeing in our experiment that is very, very weak, much weaker than the weak force. And so we still call it WIMP, because it's becoming now the name of the particle, not anymore an indication of what the physics behind, but that's, I think, the part. And then when we will know what the dark matter particle is, we will know how it enters in the structure formation and in the evolution of the universe. Dark matter particle should have been created at the same time of at Big Bang, and if they went together or they evolve, it depends if we have a single one or many, and so on. So when we will know a little bit more about this particle, we will have an idea how to introduce this in the standard model of the standard cosmological model. No, yeah.
Question in the front row.
Thanks, Elizabeth. You touched on my question just at the end of that question. What is your prediction? What is your hope? Is this one particle, or is this a zoo of particles? And if it's a zoo, what does that mean? What could that open up?
Personally, I prefer that there is a zoo, because it means that we can do much more. And also, if you think, if 25% of the matter in the universe is so complex, it's very complex. We have from these elements, we produce, something as complex as a biological structure that can be even sentient. It will be sad that the remaining 80% is very uniform. And if it's many particles, well, we need to understand how they do. There will be a lot of experiment with different way to try to understand this new. We have the chemistry of the dark matter. You see, next time the chemistry department, they will have the chemistry of dark matter. So this will be very exciting.
We've got time for one or two more questions. There's a hand up there. It's coming. That microphone's coming.
Hello. I have a question that I've always had since I was in high school, that the lighter is the body, the slower it goes down. Now, tonight you are saying that the dark matter is not that much, so is it any chance that the gravity is not a thing, but we are pushed down from the dark matter?
Okay, so there are hypotheses that in reality, the dark matter is not there, but the gravity, as we know, the theory of gravity, especially the general relativity, is general gravity, so the one that brings the universe together, is maybe.
I'm talking about the Earth gravity.
No, we cannot. Okay, Earth gravity cannot catch dark matter, because dark matter. So, to slow down something, you need to have a force. You need to pull or push to move something. And if dark matter cannot be pulled or pushed very much, except gravity, it doesn't really, it doesn't do very much. The gravity, the particle we are speaking is something like at the subatomic level. So the gravity is really very, the gravity force is very, very limited there to be something that it can work at large scale where we have a huge amount of dark matter, and so you see the lump of dark matter, but dark matter doesn't get trapped. Well, theorists can say that there are some model in which you can trap for some interaction, but if you look at the vanilla model, I say that single particle and so on doesn't get slowed down or produce any structure.
We have time for maybe one more question.
How does dark matter interact with dark energy? How they, influence each other?
We don't know. Dark energy is even more mysterious than dark matter. Dark energy is really like we are really in the dark, to make a very bad pun. While in dark matter, because there is the gravity, at least we have some hypotheses and we have that. In dark energy, we really don't know how to build the experiments. There are a lot of, experiments but you need to restrict very much the hypothesis. So, yeah, one dark at a time.
And on that note, I'd like you all to join me in thanking Elisabetta Barbera. We look forward to seeing you again next week for the second of the July lectures, and please have a safe journey home.